Good afternoon, everybody. As happens this time of summer, every summer for the last 50 years, Lance comes and brings students with him. Tyler and Alex, this is the third year they've come here, and they're working on their PhD, and we're going to have a tag team seminar today. Each one will speak for only 25 minutes, right? and then we'll ask questions and stuff, and then we'll move on to the next one. I should also remind or let everybody know that Lance Bozart will be giving a seminar Tuesday morning at 10 o'clock. I'm going to have to get up extra early for that one. I might be late, Lance, but you can introduce yourself if need be. And both Lance, Tyler, and Alec will be here through next week. Lance is in room 3018, and Tyler and Alex are in room 3071. So they'd love to talk to people about NCAR and their proposed research and so forth. So we're going to start today with Alex. Alex is a PhD candidate at the Department of Atmospheric and Environmental Sciences at the University of Albany. He got his BS from North Carolina State University and moved north for his master's and now PhD because he wanted to sample snow, right? Yeah, essentially. His research interests focus on the dynamics, variability, and predictability of synoptic scale phenomena that can lead to high impact weather events. He is especially interested in investigating extreme weather in subseasonal to seasonal timescales. He must have read the strategic plan. Outside of his academic pursuits, he enjoys kayaking, hiking, and cooking. So with that, we'll introduce Alex and let him go ahead.
Thank you for a warm welcome, Morris. I'm excited today to talk about the atmospheric dynamics governing the recurvature of eastern North Pacific tropical cyclones. I'd like to first acknowledge my co-advisors, Kristen Corpiciero and Lance Bozart. And I'd also like to acknowledge my funding source from the National Science Foundation, not only for supplying funding for my PhD, but also my master's as well, since I've been at Albany. So just to get started, I like to always bait with the case when I start some of these presentations. And in this case, I want to bait you with a tropical cyclone that formed in 2023 in the latter end of the TC season in the eastern North Pacific. This is Tropical Cyclone Lydia. What was interesting about Tropical Storm Lydia, and just in association with this talk, is that this system formed about October 3rd and dissipated around October 11th once it made landfall in the state of Jalisco in Mexico. What was interesting about this system is it formed and recurved. One of the interesting aspects of that is that it underwent rapid intensification, and that RI occurred just before landfall as well. So they don't always have a lot of lead time in some of these situations. And in this case, this posed a significant threat to the folks over land. And so I just thought it was very interesting and to motivate this perspective, because you don't often see RI after recurvature. You usually see the opposite. But with that being said, I would like to go ahead and start by outlining the talk. In this case, we'll just give some background information about tropical cyclone motion and eastern North Pacific tropical cyclones as a whole, follow with the methodology that I use to do clustering results for understanding the overall spatial variability of tropical cyclone tracks in the eastern North Pacific, along with large-scale composites that I form and construct using the recurving tropical cyclones within these clusters. And then I'll finish out with a case study to highlight the complexity of the flow patterns that can result from these systems, and conclude with some final remarks. So some of the background information here with tropical cyclone motion, as we know, TC motion is largely governed by synoptic steering flow. And when I say that, I primarily mean looking at the variability of subtropical ridges and upper-level mid-latitude troughs or potential vorticity disturbances, along with differences in the subtropical jets. And also, we've seen in the previous literature that storm intensity, size, depth, beta gyres, convection, and microphysics also play a large role in how TCs tend to move along their different tracks. And just to give some further background information about the eastern North Pacific, TCs are generally observed between June and November, and they typically peak from between July to September as well. So this is important to keep in mind when we think about conditional probabilities for TC formation and also how we can get recurvature as a whole in this part of the world. So one of the main questions I want to highlight in this particular presentation is, what are the unique TC track distributions in the Eastern North Pacific, and what are the associated large-scale atmospheric wave patterns that influence these recurving EPAC systems? So in order to describe the spatial distributions of tropical cyclones in this basin, I adopt a clustering technique from Nakamura et al. 2009, in which they utilized the HERDAT2 database as well as I did as well too, for storms that reach at least tropical storm intensity. I cluster these tracks with a k-means clustering approach using the first and second mass moments that are defined below. What these two different mass moments overall do is help to preserve the shape, track, and the length and location while clustering. So for the first mass moment, we kind of give a perspective or an idea of the location of the TC tracks themselves, along with the actual curvature or the shape of the track as we define with the mass moment too. And these are all weighted by the tropical cyclone wind speeds as defined by W. So once we're able to cluster out these tropical cyclones and look at the different variability, I then want to extract recurving tropical cyclones within these clusters. So in order to do that, I utilize the ERA 5 reanalysis to identify TC locations based on minimum sea level pressure within the reanalysis within a 2 by 2 degree domain of the observed locations shown in HERDAT2 from 1949 to 2022. So once we've identified the tropical cyclones utilizing MSLP minima, we then track along this trajectory that I've schematically shown here. And what I wanted to do first is understand the TC motion vector as a whole. So in this case, when we think about recurvature, we're thinking about tropical cyclones that are usually moving poleward or gaining latitude. And we do this every 6 hours. And in this case, the storm motion must be positive, or delta latitude must be greater than 0. And then we calculate the angle between the motion vector and an eastward reference vector. And that angle must reside between 0 and 90 degrees over a 24-hour period to suggest that the systems are typically moving eastward in this case. So once those initial points are satisfied, the criteria for all TCs are identified and stored as quote-unquote recurvature points, which I'll be using throughout this talk for subsequent analysis. So now that we have the tropical cyclone, recurved tropical cyclones of interest, and we've extracted those within each cluster, we then define all recurvature points, and I've shown this again schematically here, just offshore Mexico, for example. What we then do is calculate the TC recurvature centroid, so we have an average location in which these systems do typically recurve. And once we are able to calculate the centroid of all the recurvature points within each given track, we can then form what we call a composited TC track here. And this is going to help us to utilize time lag composites to look at the environmental flow locally and upstream as well. And we'll reference this recurvature point centroid as T0 or T0 going forward as like the onset of recurvature. So to describe the environmental variability of the chosen clusters of interest relative to recurving Eastern North Pacific tropical cyclones, we construct time lag composites, as I've alluded to earlier, of the upper tropospheric features across a predefined North Pacific domain, as I've shown here, using the ERA 5 reanalysis relative to all the TC recurvatures. And then we shift these domains, these predefined North Pacific domains, relative to the common centroid that we've quantified within each cluster, and to describe the overall variability from like a first order generalized standpoint. So here are the results that I wanted to showcase first. These are the cluster analysis using the k-means approach. In this case, I chose 4 to understand the overall spatial variability. And what you might notice right away is that on the left-hand side for clusters 1 and 3, what stands out prominently is that these systems typically do not move too far west, or at least sometimes can move poleward or even recurve in some cases. And in clusters 2 and 4 on the right-hand side, primarily most of the systems within these clusters typically move far westward, or in some cases move westward and then poleward over time. For the interest of the talk, we're going to be focusing on clusters 1 and 3 particularly, and looking at the recurving tropical cyclones that were classified within those. So once we look at the recurvatures, or the recurving tropical cyclones within cluster 1, some of the statistics that we see within this particular cluster is that the mean track length is typically about 2,000 kilometers with the average translation speed of about 3.85 meters per second. And if we compare that to cluster 3, where we do the same kind of recurving extraction, we notice 2 different things. One, we notice that the centroid, or the recurvature centroid, is much further north. And that has implications about where you might get an expected landfall potentially. And what we also notice is that the track length is about 1,000 kilometers longer, and it has a faster translation speed of almost about 5 meters per second. So this has some implications about how it interacts with the environmental flow as well. When we look at the temporal distributions between these clusters, looking at just recurving tropical cyclones, one of the things you notice is that for clusters 1 and 3, you typically see a bimodal distribution throughout the TC season, one maxima being towards the early part of the season, or like mid to late May and early June, as well as in September and October towards the latter end of the season. But you see a minima towards July and August before you see the rapid ascension in occurrence. And what's really interesting about this is that cluster 1 typically has a peak around, let's say, early to mid-October compared to that of cluster 3, which has a higher frequency and peak towards September instead. So now I want to go over the time-lag composites that I mentioned earlier. So here we're looking at the onset of the recurvature using the composite analysis that I alluded to earlier from my methodology. So on the left-hand side, we see 500 hectopascal geopotential height anomalies, which are shaded in units of meter, along with 500 hectopascal geopotential heights and contours. On the right-hand side, we have 250 hectopascal zonal wind anomalies that are shaded, along with the 250 hectopascal wind speeds and contours. So just to look at the left-hand side here, one of the things that you notice between both clusters is that there's typically an upper tropospheric trough in proximity to these tropical cyclones. Therefore, if we look at the right-hand side, just thinking in comparison to the left-hand side, you also see an entrance region of a subtropical jet as well. What's interesting about this is that while these might be comparable at the onset, their pathways and evolution look a bit different. So that's what we're going to do now is explore clusters 1, the recurving tropical cyclone first order scenario going back 5 days. So we'll start here. These are the same plots again, but the stippling in both of these plots indicate areas where the anomalies are statistically significant at the 95th percentile using a t-test. So one of the things, I've pointed out some features within these composites. So if we look at the left-hand side, one of the things that I noticed right away is that you see 5 days prior to recurvature, a Bering Sea trough and a Gulf of Alaska troughs that drape across the North Pacific. And on the west coast, you see an amplified ridge just prior to recurvature. And on the right-hand side, we see an extended North Pacific jet, and particularly the exit region is predominantly focused around the Gulf of Alaska. If we step forward in time, what's interesting about this is that if we look at the left-hand side, for example, the Bering Sea trough that I pointed out earlier begins to deepen, and the Gulf of Alaska trough begins to weaken as the West Coast ridge amplifies. And if you look at the North Pacific core, or North Pacific jet core, that also strengthens along with that deepening trough upstream. Over time, the Bering Sea trough continues to deepen, and the West Coast ridge actually just begins to shift poleward over time. And noticeably, as you can maybe see here, if we go back and forth, the North Pacific jet core also extends eastward over time. So really, we're seeing an intensification of the North Pacific jet and an eastward extension along with that as well. By the time we get to 2 days prior to recurvature, that Bering Sea trough continues to deepen, West Coast ridge continues to shift poleward, and now we see a short wave trough, or a trough that over Gulf of Alaska that weakens but begins to move eastward as well over time. And then the North Pacific jet core also continues to strengthen and then begins to shift poleward. So now we see an amplification of North Pacific jet, an eastward extension, and then a poleward shift. This is 1 day prior to recurvature. And again, Bering Sea trough continues to deepen, but the Gulf of Alaska trough that I mentioned earlier turns in, or at least manifests in this composite as a shortwave trough. And that undercuts the ridge that was amplifying and migrating poleward over time. And again, you can see if you look at the tilt or the axis of the North Pacific jet, it's tilted poleward in this particular composites. And then you see a subtropical jet near the eastern North Pacific become more established. And finally, by onset, you could see that the subtropical jet offshore of Baja California in proximity to tropical cyclones from cluster 1 that recurve is also enhanced as well. So that kind of helps to impart some westerlies in the flow as well. So if you go to cluster 3 instead and do the comparison, we're going back 5 days again, you don't see as much of an amplified pattern right away. Actually, one of the biggest differences between cluster 1 and 3 is the presence of a subtropical ridge over Mexico. That subtropical ridge is partly a climatological signal. As we can recall, the peak occurrence of these systems occurs around September. So when you can get a subtropical ridge over Mexico as such, you can then get the steering in such a way that the cyclones that basically meander or steal around the subtropical ridge initially before a trough ends up interacting with those systems as we saw in the onset composite. But nevertheless, when we look at this, we can notice the split flow regime over Western North America, along with the Western Pacific trough that's in the lighter blue colors there over the West Pacific. Over time, that western North Pacific trough deepens, and we see that that ridge trough couplet over western North America begins to propagate eastward, and yet we still see the maintenance or the subtropical ridge that I point out persist throughout this time evolution. Nevertheless, what we also see in comparison to cluster 1 with the right-hand side is that the North Pacific jet does strengthen in this case, but if we step to T0 minus 72, what's interesting about this is that while the North Pacific jet strengthens, we still see the persistence of a subtropical jet offshore Baja California. So I'll go back one more time to 5 days and we'll step through. Notice that you still see the subtropical jet persistence within this composite, unlike what we saw with cluster 1 where it really wasn't well established until right at onset. Finally, when we get to minus 2 days, what's really interesting if we focus back in the Western Pacific and the Central Pacific, looking on the left-hand side here, the trough that we mentioned earlier in the composites, the Western North Pacific trough deepens and then helps to build or at least produce a Gulf of Alaska ridge. And that begins to amplify, and what we see is indicative of downstream baroclinic development across the North Pacific. And then finally, we see what's really interesting between the -1 and onset days is that when you can get this amplified Gulf of Alaska ridge, you also get an anticyclonically curved jet to the north as well. So that changes the positive vorticity advection and cold air advection that you would imply as well based on how that amplification occurs. And then you could see just at T onset, the East Pacific trough then deepens, and then that's what we saw earlier in the composites. So just to give a quick summary, since that was a lot, cluster 1 depicts the formation of a deepening trough of the Bering Sea leading up from day -5 to day -2. And that deepening Bering Sea trough then enhances the upper troposphere geopotential height gradient and shifts the North Pacific jet poleward by day -2, or 48 hours. As the North Pacific jet strengthens into the Central Pacific, a shortwave trough undercuts the amplifying Western Canadian ridge and deepens over California. The aforementioned shortwave trough leads to the development of a subtropical jet entrance region over Baja California in proximity to these recurving systems in cluster 1. Similarly, if we do a summary of cluster 3, what we're seeing is an indication of downstream baroclinic development from day -5 to day -48, if you think back to the trough ridge, trough structure that I had noted earlier. In response to that downstream baroclinic development, the North Pacific jet transitions from a climatological regime to a more poleward shifted regime with its exit region featuring that really enhanced anticyclonic curvature and jet core maxima just upstream, shifting over the Gulf of Alaska by T0. And then an EPAC trough, of course, forms and deepens downstream of that amplifying Gulf of Alaska ridge, thereby reinforcing the subtropical jet centered over Baja California in proximity to the recurvature point of TCs in cluster 3. So what I want to do now is pull quickly a case study and highlight some of the complexity of the flow patterns in these composites. In this case, I'm motivated to look at two tropical cyclones that occurred in 2018 from this particular cluster. And I'm going to just show like a summary plot here of those two tropical cyclones. So we'll first focus over the eastern North Pacific. Here in the orange and purples, we have tropical cyclones Rosa and Sergio, which both recurved and moved inland and made landfall over Baja California, as suggested by the cluster analysis. If we look upstream, there was also some other tropical cyclones of interest here that had some interactions with the flow. Particularly, we had a rare recurving tropical cyclone Walaka over the central North Pacific, as well as over in the western Pacific, we had typhoons Trami and Congreve, which also recurved and underwent extratropical transition. I have also plotted the SST anomaly, so you could see some of the residual effects of upwelling from these tropical cyclones that moved over warm waters, and you can see that here in this cooler SST anomalies over the WestPAC, and of course, over the EastPAC. This is really important too, because in order for systems to maintain themselves during recurvature, you do need higher SST anomalies to maintain their intensity and structure overall, unless they go non-tropical, of course. And in this case, you could see there was a positive warm anomaly in the SSTs just off Baja California, so that had some interesting implications about their tropical characteristics. If we look at the highlighted flow or the large-scale flow across the hemisphere during this time period, here in the on the left-hand side, we have 500 hectopascal geopotential height anomalies in sigma coordinates, and on the right-hand side, we have the dynamic tropopause V1 anomalies in meters per second. This is a Hubmuller constructed from 30 degrees to 60 degrees north, extended from September 15th and going down to October 15th in time. And one of the things that I noticed right away is the excitation, or at least an amplified Rossby wave train that initiated sometime around September 27th and moved eastward into the North Pacific by October 5th. And really what's interesting about this, if you look at both figures, is that in the end, if you can get a wave train to propagate in the North Pacific, at times if you can get recurving tropical cyclones, if they undergo extratropical transition, they can actually further amplify the flow even more. So one of the other things I want to mention and bring about, and this is an important detail as well too, is that we had an active MJO. And in previous literature, we know that MJO phases 8, 1, and 2 are statistically significantly linked to tropical cyclone genesis in the eastern North Pacific. And in this case study, we can see by the time September 22nd arose, we had an active MJO phase 8. And then, of course, that propagated into phase 2 by October 9th in this case. So the next thing I'm going to do is show a suite of maps. And in this case, we have shaded the 250 hectopascal potential vorticity, PVU units, along with the 250 hectopascal irrotational winds in the green vectors that I have plotted above it, along with the 500 hectopascal vertical ascent. And I also have all the tropical cyclones of interest in this domain too. And you can tell this is a fairly active time period. You have 2 tropical cyclones in the western North Pacific. You got one that's moving into the central Pacific. And then you have tropical cyclone Rosa at this time over in the eastern North Pacific. So over time, we're going to step through 1-day increments. We're starting at September 29th and 18Z. If we step forward in time, what I want to focus right now is on the tropical cyclone Trami in the western North Pacific. As this system moves poleward over time, its moisture is advected poleward, and you could see a divergent outflow or amplified divergent flow ahead of the system and helping to advect PV. And this is really interesting because by the time we get to October 1st, now we see a much more amplified flow. And I'll go back and step through this again. So if you see really quickly, Rosa is also on the eastern North Pacific moving poleward as well too. And this is important because now you see 2 or honestly 3 distinct ridge features as well as 2 troughs that are over the central Pacific. And this is really not the most common scenario you would see in this time of the year, in my opinion. What's really interesting about this is that trough over the eastern North Pacific helps to bring in TC Rosa, and then you also see anticyclonic wave breaking upstream over the western North Pacific, and that helps to fracture off this PV anomaly over the central Pacific as well. So what this looks like, where it manifests that in the geopotential heights, is a cutoff low essentially. This cutoff low, or this in this case, this higher PV that fractures off the main waveguide helps to advect tropical cyclone Walaka poleward. And this is really interesting because we don't often, again, we really don't often see this in a rare case like this, but nevertheless, tropical cyclone Walaka continues to propagate poleward. And then you again begin to see anticyclonic wave breaking over the eastern North Pacific. And really what you end up seeing at this point in time is a difference in the trough structure. So you see what looks to be like a higher PV filament or tongue, or what we call PV streamer, that helps to redirect or change the directional flow of near tropical cyclone Sergio, which is highlighted in purple there. So over time, we see that the Central Pacific Trough, we're going to step back to October 8th again. We can see that the Central Pacific Trough kind of takes over at this point. And you can see even ahead of that trough and near like the Gulf of Alaska, there's divergent outflow with moisture surges going poleward. And then you can see another introduction of anticyclonic wave breaking over the eastern North Pacific. You can see that here in the anticyclonic curl of the PV here. So again, this is one of those unique time periods in which you can get recurvature of a system based on the differences in the flow during this time period. And this is for, again, this is for 2 different consecutive cases under different influences as well. So just to give a case study summary quickly, the extratropical transition of tropical cyclone Trami triggers a western North Pacific anticyclonic wave break-in, which then leads to the development of an East Pacific trough that subsequently guides tropical cyclone Rosa inland. That same wave break-in also contributes to the formation of a Central Pacific cutoff low and then steers TC Walaka poleward and also undergoes extratropical transition. And then finally, the consecutive resulting wave amplification comes from tropical cyclone Congre, which then and again enhances a Westpac ridge and leads to the formation of a Central Pacific trough. That same Central Pacific trough then facilitates anticyclonic wave breaking near the Gulf of Alaska and produces a PV streamer that guides TC Sergio inland. So I just want to give some quick final thoughts, but what we can see from the case study at least, and this is some things that I want to continue to explore a little bit more on, is focusing on the frequency and characterizations of Rossby wave breaking over the North Pacific as a key dynamical factor in perhaps predicting recurvature of EPAC systems, as highlighted in this particular case study. And of course, as Morris has alluded to, one of my research philosophies, of course, is to enhance the prediction accuracy from a subseasonal to seasonal standpoint. And really what I want to be able to do at some point in the future is to integrate further the traditional weather forecasting with the seasonal climate predictions to improve our overall forecasting as a whole. And again, there's all these little, like what my advisor likes to say, bit players that can cause problems. And it's something that we have to be able to interlink between the climate and the weather interface. So I'm just going to leave my conclusion slide here. And if you want any more information about my research or want to reach out, you can feel free to visit my website at below. So thank you.
Thank you. Thank you. We have time for some questions. Howie first.
What fraction
Oh.
what fraction of Eastern Pacific tropical cyclones don't undergo recurvature? And I assume those are the tropical cyclones that either move and propagate westward only to die somewhere.
Yep.
And the others started by moving off to, with an eastward component.
I would say on a climatological basis, about 10% of total tropical cyclones in my time frame that I've mentioned here with my cluster analysis, I would say about 10% of those recurve on average.
All right, thank you. Very nice presentation. So I think most of your analysis was on Northeastern Pacific Basin.
Yes.
Have you looked into other basins like Northwestern Pacific or North Atlantic? And in that case, were there any other pattern, like other than the upper level jet and the trough reach?
I haven't explored those particularly, but other researchers have. What's interesting about this is that when you can get peak frequency of recurving Eastern North Pacific tropical cyclones, you often see the same frequency occur over the Western North Pacific and Western Atlantic around the same time frame. And that's partly just due to the fact that you can get these amplified wave trains during this time of the year where you can get cool air surges off of Siberia, for example. But I do believe that, and when you look at, so for example, Heather Archambault's work, looking at the recurvature of tropical cyclones over the Western North Pacific, when they go forward in time with their composites using a similar recurvature format, and you can still see that there's this enhanced ridge building over the West North Pacific that leads to a Central Pacific trough. And in this case, we had a tropical cyclone over the Central Pacific, so that kind of changed some of the our canonical way of thinking about the flow variability. But again, this is some similar patterns that we see with other basins. But again, what I want to emphasize here is that they're all interlinked in some ways too. And in this particular case, they're very interlinked. But there's a lot of conditional arguments to be made as well, right?
I just had, I think, 2 questions very specifically about the k-means clustering, just out of curiosity. So the first one, it sounded like you used kind of 2 different metrics for the k-means clustering, like one of them being, or eventually when you do these center composites, one of them being maybe the location of the cyclone and its track as well. So just confirming that. And secondly, what you added some kind of weight. You mentioned a weighting for the wind speed, and I'm curious what was the purpose of that and what exactly it did for you in this k-means clustering.
Sure. Yes. So one of the things from this adopted k-means clustering approach is that I did weight it and didn't weight it too. And it does produce some interesting or different results, I would say. So when I weight it, I find that it was better at aggregating specific clusters based on their characteristics versus when I didn't weight it. And one thing I didn't probably mention before is I also have to standardize all these variables as well too, to a mean of 0 and a first standard deviation. But really, this k-means clustering is a fairly simplistic way of looking at it. What we're doing is just preserving the actual centroid of the actual track that we're looking at, and then just seeing what the variance along that track looks like, because we want to be able to preserve the shape itself too. So yeah, I think that hopefully that answers your question.
Well, let's thank Alex again for the first half of the tag team. And you'll be able to ask more questions after the tag team seminar over by the cookies and whatever. Tyler is next. Tyler Leicht is PhD candidate, University of Albany, with Lance Bozart. His PhD research focuses on wintertime persistent flow regimes across the Northern Hemisphere, applying synoptic dynamic meteorology to questions of large-scale variability. He got his BS from Cornell University in 2018 with a minor in climate change, MS from University of Albany, and now is working on his PhD. His hobbies include playing the oboe, baking, and running. And with that information, we'll let him describe what he's going to talk about.
All right, thank you very much, Morris, for that introduction. Hello, everyone. As Morris said, I'm Tyler Leicht. I'm a sixth-year graduate student working with Lance Bozart at the University of Albany. And today I'd like to talk to you about a sort of overview of a good chunk of my PhD work, which has been looking at Northern Hemisphere wintertime persistent flow regimes. And in this talk, I'll be linking that to the Madden-Julian oscillation, as well as variability of atmospheric rivers. I'd also like to just thank my funding source, which has been the Center for Western Weather and Water Extremes, which is located at the Scripps Institute for Oceanography. So broadly speaking, the motivation of what got me interested in these large-scale weather regimes, given that I have more of a traditional synoptic dynamic background for my work, has been through my master's thesis and by looking at more regional blocking patterns and trying to characterize persistent ridges over Western North America and in the Eastern North Pacific. Oftentimes, they were linked to concurrent flow anomalies across the entire Northern Hemisphere. So that got me thinking about how I could possibly identify and understand some of these patterns that have a larger, more planetary scale extent to them. When we think about the study of weather regimes, broadly speaking, in the literature, oftentimes they will focus on more regional patterns, such as over just the North Pacific or just over the North Atlantic. Oftentimes they'll attribute all or most days to a weather regime. So rather than just selecting for the most high amplitude patterns, you'll get sort of a mix, and that can sort of muddy up some of that analysis. As well, they'll typically use some sort of EOF analysis to initially smooth the data so that they're just extracting the larger scale features. But given the interest in looking at some of the dynamical mechanisms, I wanted to preserve that as much as possible in my study. So broadly speaking, this dissertation aims to identify high amplitude, quasi-stationary, Northern Hemisphere scale persistent flow regimes, or PFRs, as you'll see them referred to throughout the talk. Analyze how the persistent flow regimes can form and develop. That's sort of been the first chunk of my work, which will not be shown today. And today I'll be connecting these flow regimes to teleconnections and synoptic weather impacts. And maybe just to show that a little bit schematically, I've already done some look at some time lag composites similar to what Alex just showed of how these types of flow regimes can set up on these longer timescales. And today I'll be focusing on relationship with teleconnections, mainly the MJO, and then relation to surface weather, mainly atmospheric rivers. So just to briefly identify how these flow regimes are identified, I'm using 500 hectopascal standardized geopotential height anomalies from the CFSR just for DJF, since I'm concerned about wintertime weather regimes. These persistent flow regimes are identified by widespread concurrent positive and negative standardized geopotential height anomalies that persist for at least 7 days. And this is sort of a modification of Dolan-Gordon's persistent anomaly criteria that was established in the 80s. I won't go into too many of the other additional criteria that go in, but I'm happy to talk offline if you really want to get into the nuts and bolts of how I whittled down some of this to identify the weather regimes. From there, by establishing this catalog of weather regimes, they're then grouped and composited using k-means clusterings for k equals 5 nodes. This is more based off synoptic intuition, given that several different quantitative testing for an ideal number of nodes were fairly inconclusive. So after all this, these are the composite patterns that we see for all 5 of these different clusters. As you can see, there's roughly about 20 to 25 events in each of the clusters. And the other sort of reassuring thing after doing this analysis is that there are familiar patterns of more established low frequency variability that you can see through this identification. So if we look here, I should say these are going to be labeled cluster 1, 2, 3, 4, and 5. So if we look here at the top center at cluster 2, that's going to be very similar to a negative NAO type pattern. If we look here at cluster 4, this has a very strong Scandinavian blocking signature. But the other nice thing about this analysis is that there are other novel features that aren't captured in some of those other more classic definitions, more indicative of a Rossby wave drain. And so that's nice that it adds this additional layer of analysis that we can see through the work. Like I mentioned previously, I will be, in this first part, linking between the persistent flow regimes and sort of the frequency of various phases of the MJO. I'm using the RMN index as defined by Wheeler and Hendon in 2004. Broadly speaking, the first part of the analysis will be looking at frequency of MJO phases relative to the life cycle of these regimes. So I will be looking at 2 one-week intervals before the start of the regime, during the regime itself, and then 2 weeks following the regime to try to get a sense at more of this long duration sort of S2S type variability that might be influencing these regimes. Along with that, statistical significance for the frequency anomalies relative to that life cycle is assessed through bootstrap resampling. And on those plots, you'll see sort of red and blue stars that'll indicate statistically high or low frequencies. Just as a reminder for everyone, just to get a sense at where the MJO convection is sort of located across the tropics during each of these phases, I've got this schematic down here denoting the rainfall anomalies that are typically associated with each phase. And as a bit of a spoiler, you'll see phases 6 and 7 pop up a lot, and that's typically indicative of enhanced convection sort of in the West Pacific and Central Pacific, respectively. Another part of this work is to try to assess the potential tropical extratropical interactions that may be happening and how that can influence the actual amplification of the flow regimes. So in order to get at that, I employed this metric of a stationary Rossby wave number as calculated in Henderson et al. 2017. And this will essentially set up a way of looking at the potential waveguide for Rossby waves generated by the MJO convection. These two equations down here are what are being calculated. Just to summarize, this is essentially a gradient of absolute vorticity, such that this K sub S, wherever it is going to be maximized, that's going to be an effective waveguide for the most scales of Rossby waves. So you want to see a higher number to see both planetary and more synoptic scale waves being able to propagate along that medium. So what I have here is one of these figures that I generated for this, again, showing the 5 different time periods relative to the life cycle of the regime. So this is going to be during the regime, a week prior, 2 weeks prior, and a week after, and 2 weeks after. This is for cluster 5, and this one was chosen just because this is a really good example of the more widespread statistical significance, where it seems as though the MJO really does have these anomalous frequencies relative to the life cycle of the regime. The other nice thing, if we kind of zoom out and see the bigger picture here, is you can see sort of a coherent propagation of these increased and decreased frequencies as assessed through the statistical significance. So if we look here in the 2 weeks prior to the formation, we see an anomalous frequency of phase 5 and 6 of the MJO. And as we get closer and closer to the regime, it starts to propagate eastward as you expect for the MJO. So that also adds a little bit of physical credence that there's a more dynamical phenomena that's being captured by these statistics here. On the flip side, if we were to look at cluster 4, which I mentioned previously, that's more indicative of Scandinavian blocking and seems to be a bit more of a higher latitude regime. There's much less statistical significance before the persistent flow regime formation. So really only in the week prior is there any sort of anomalous frequency of the MJO that we might be able to use to try to tease out in sort of a situational awareness way of the likelihood of one of these regimes forming if we know that there's an active MJO event in certain phases. And this is also mostly just brought up to show that there's quite a bit of variety between the different clusters. So it's not as though the MJO is highly anomalous for all of these different types of regimes relative to its life cycle, but it can vary quite a lot as well. And in addition, I just want to mention that there is a similar sort of propagation of the frequency anomalies, such that you're going from phase 6 to 7 and staying in 7. But you will note that this is a much slower propagation, so again, could also hint at potential differences in propagation speed of the MJO itself as well. One other thing that was sort of interesting that came out of this is if you were to compare for 2 different clusters, so this is going to be cluster 2 and cluster 5 here, and you look at the same lag time between them in the week preceding the formation of these regimes, you can see that the same phase of the MJO is significantly more likely to occur. So you can see phase 7 here for these 2 particular examples is anomalous to occur. And another note, just because I won't be able to show all 5 clusters in this, all 5 of them have some enhancement of phase 6 and/or 7 preceding the formation of the flow regimes. So that suggests that maybe this West Pacific convection might be a very conducive mechanism across all of the different regimes for the amplification. But getting back to these 2 examples, what was interesting about this is given you have an enhanced frequency of the same phase of the MJO at the same exact time, but you're resulting in 2 very different patterns, it starts to question what might be going on dynamically to explain why you might have these 2 different pathways occurring. So that's where we're getting at these types of composites showing the stationary Rossby wave number. So that metric here is going to be in this green to yellow shading. And again, the wave number itself is going to be representative of the actual zonal wave number of the Rossby waves that could travel in these regions. Along with that, we have the 250 hectopascal winds for these composites in the black contours. And the anomalies are, rather than relative to a more traditional climatological base state, they're relative to other MJO phase 7 events. So rather than saying it's anomalous relative to wintertime conditions, it's now anomalous relative to similar MJO events to, again, see what might be happening different for these exact examples compared to other comparable MJO events. And what we can see, broadly speaking, is, well, first of all, sort of zooming out, we can see that, broadly speaking, there are positive wind anomalies within both the North Pacific and the North Atlantic jet cores in some vicinity. So that's suggesting that overall, big picture, the flow is more, you've got faster jet speeds overall in these periods relative to comparable MJO events. The other thing that you might notice is some of the subtle differences here, especially in the exit region of the North Pacific jet, are shown here between this cluster 2 and cluster 5. So what you can see in cluster 2 is the 30 meter per second contour extends a lot further, and you've got a much more gradual jet exit region here in the composites. When you compare that to cluster 5, you've got this much more strongly sort of anticyclonically curved jet in the composite, and it's got a much more abrupt jet exit region sort of around 150 west. And if I were to sort of trace along the potential waveguide for where the Rossby waves could be emanating, we can see that they're quite a different pathway between these 2 examples. So in cluster 2, if you were to sort of excite any Rossby waves with this convection, sort of here in the West Pacific, that would travel pretty much right around 30 to 40 north. And then right here around 135 west, it would come up and over this ridge here in across North America. So the Rossby waves would enter the mid-latitude flow guide somewhere around the coast of Western North America. If we look here at cluster 5, however, you can see that because of that anticyclonic curvature and this anomalous sort of more subtropical jet here across Mexico and the southern US, the possible pathway for the Rossby waves to enter the mid-latitudes is going to be much more over the Atlantic sector. So even just the characteristic of the mid-latitude flow itself is going to determine where the possible tropical, extratropical interactions would set up in these composites. So just to briefly summarize that chunk of work, These persistent flow regime clusters often share increased frequencies of phase 6 and 7 of the MJO, preceding the formation of these regimes. That seems to be a commonality amongst all 5 of them. Along with that, the overall just mid-latitude flow pattern seems to be anomalously strong in these examples. So you've got enhancements of both the North Pacific and North Atlantic jets preceding the formation of the ridge, of the regime, relative to other comparable MJO events. And then along with that, when we're trying to think about the possible pathway for Rossby waves, the orientation and the strength of the North Pacific jet stream exit region is really what sort of dictates the potential pathways for these Rossby waves emanating from the MJO convection to enter the mid-latitudes. So now I'll be shifting towards that other portion of my work in linking between these persistent flow regimes and the frequency and some of the characteristics of atmospheric rivers. So atmospheric rivers will be identified using the Guan and Walliser AR database, and this is based off air interim data. The first sort of initial set of analysis will be assessing the anomalous frequencies of atmospheric rivers across the hemisphere in both the 2-week period preceding the persistent flow regime and for the duration of the flow regime itself, to just see how these types of large-scale patterns can influence the frequency and variability of atmospheric rivers. Later on, I'll also have statistical significance. That's just using a 2-sided t-test. And as well, I will be looking at atmospheric river characteristics, and that'll be between atmospheric rivers that are and are not associated with a particular persistent flow regime. And so those AR time steps will be taken from this subdomain focused over the Eastern North Pacific and Western North America from 110 to 140 west and from 30 to 50 north. So just to orient everyone, since I know not everyone is super familiar with the sort of frequency and climatology of atmospheric rivers, here is a DJF climatology from the Guan and Walliser database. These percentages down here are going to be of all DJF time steps. So what you can see is, broadly speaking, in the storm track regions, you have anywhere from 10 to upwards of 15% of all DJF time steps are going to be associated with an atmospheric river. Another characteristic specifically of the Guan and Walliser database is that it has a more permissive threshold for what might be considered an atmospheric river. And so that helps you to capture more inland penetrating atmospheric rivers that might fall below the integrated vapor transport threshold that's often used in other detection tools for atmospheric rivers. So that's why you can see an extension here across interior North America as well as Eurasia of a lot of these atmospheric rivers during DJF. So like I mentioned, we'll be looking at all 5 clusters at the anomalous frequency of atmospheric rivers in the 2 weeks preceding persistent flow regimes. So again, still oriented, so it's clusters 1 through 3, and then 4 and 5 here in the second row. Generally speaking, what we can see is that there's pretty large frequency anomalies relative to climatology. So especially on the sort of periphery of the storm track regions, you can have anomalous frequencies of up to sort of plus and minus 10%. So relative to the climatology, that's almost a doubling or almost elimination of any AR activity happening in these regions. And generally speaking, across all 5 of these clusters, the anomalies represent a shift in the storm track across both the Pacific and Atlantic basins. So generally, it's going to be sort of a latitudinal shift. And when we're thinking about North America, typically that'll manifest as sort of deflection here in cluster 3 towards Alaska, maybe towards British Columbia, or even this sort of atmospheric rivers that are more anomalous off the coast, but then become more climatological near the coast in the case of cluster 5. When we look actually during the persistent flow regime, so sort of between the start and the end times, we can see that generally the anomalies will mirror the period preceding the formation of the regime. So that suggests that maybe similar dynamics are at play, but they're not quite as strong. And so the overall hemispheric flow pattern hasn't quite locked into place. But you still can have these extended anomalous periods of enhanced or suppressed atmospheric river activity. That would be important to know as we're thinking about these more weather events on longer S2S timescales. One notable exception of that suggestion that a lot of the similar patterns are here but more amplified is across the western US before and during cluster 2 persistent flow regimes. So as you can see here, it's near climatological when you're during one of those regimes, but actually in the lead up, there's sort of this anomalous trough that lingers around, and then by the time you start up the regime, flow becomes a lot more zonal in this region. And so in the period leading up to it, you've got enhanced atmospheric river frequency, but then during the event, it goes back towards climatology. Morris?
What's happening up the northeast quarter there?
In cluster 2? Yeah, so essentially cluster 2 represents, in the Atlantic sector, it's reminiscent of a very strong negative NAO. And so you've got a split jet, but predominantly towards the south end. And so especially with sort of the downward extension of the eddy-driven jet, that can really pick up on atmospheric river anomalies. And I'll get to that a little bit later, but oftentimes this anomalous low-level winds can manifest as the IVT that gets counted in the atmospheric rivers rather than just the moisture source itself. So that's actually a great segue, Morris. Like I mentioned before, considering that my funding source comes from Southern California, I was interested in sort of these periods of enhanced atmospheric river activity that might be of importance to their water resources as well. And so of that, that's going to be the cluster 1 regime. So again, I'm interested in sort of the characteristics of what these atmospheric rivers might be looking like when they're during a cluster 1 regime versus when they're in a more progressive flow pattern that's more climatological. And on the right here is just the overall height field of these types of regimes where you've got this predominant trough here just to the south of Alaska, a ridge over British Columbia, and sort of this implied split flow again here near Western North America. So what we're looking at here is going to be atmospheric rivers that are subtracted from, we're going to have ARs that are associated with it, and then subtract from that the non-regime atmospheric rivers to get a sense at what is anomalously high or low for these particular set of atmospheric rivers. So when we look here at the IVT anomalies, so that's typically the metric used for defining atmospheric rivers, you can see that there's this extension across the North Pacific from 30 to 40 north of the IVT, flanked by these anomalously low values sort of within the trough itself, and then to the south side, sort of on the anticyclonic shear side of the jet. You can also see the implied split flow here as you've got enhanced IVT all the way into sort of central Canada during these events as ARs might be making landfall in British Columbia and extending inward, as well as some of the more subtropical events that are here occurring in Southern California and across northern Baja. Another thing to note about this is this very neatly mirrors what we saw in the actual frequency anomaly, so that seems to be what's really driving is this anomalous IVT. When we think about integrated vapor transport, it's got a moisture and it's got a wind component to it, so I wanted to disentangle that to see what might be happening differently in these events. So what we can see here is when we look at precipitable water, really the only positive anomalies that are associated with this IVT are again in this central Canada location and as well as sort of coastal California. So that's indicating that perhaps we're not tapping into a really deep, rich moisture source, but it's a lot more locally driven. Whereas upstream, you've got anomalously low precipitable water. So that's suggesting that the air masses over here are probably going to be colder and more associated with that trough itself rather than any sort of subtropical East Pacific air masses. And then, like I mentioned earlier, IVT can also be sort of have a footprint from the wind field. So what we can see here is for the 850 hectopascal wind anomaly, we can see this anomalous sort of low-level jet here around 150 west, and that's upwards of about 3 meters per second stronger than what you would get for a more typical progressive flow pattern in those atmospheric rivers that might be happening at those times. Just to look a little bit more broadly at the atmospheric conditions, I wanted to look at the mean sea level pressure. And as you can see here, pretty much anywhere north of 40 north, you've got anomalously low pressure here on upwards of about 8 hectopascals. So again, what's happening here is suggesting that there's sort of stronger parent lows that are going to be associated with those atmospheric rivers. And so there might be, just generally speaking, a stronger dynamical component than a thermodynamical component when you're thinking about the impacts of these ARs as well. And then just to round out, to look at the upper level jet to complement the low level jet, what you can see here is, again, the upper level jet is going to be a little bit equatorward shifted. It's quite a bit extended. And as it approaches the coast, at least in this anomaly framework, it takes on this northwest to southeast tilt. So again, suggesting that you're not getting any sort of southwesterly flow that would tap into a richer moisture source. These are going to be sort of more wind-driven and a lot drier events. Just to briefly wrap this up, we can see that up to 2 weeks prior to the formation of these regimes, you can see AR frequency anomalies of up to plus and minus 10%. When looking at the subset of atmospheric rivers that are associated with this cluster 1 persistent flow regime in the eastern North Pacific and western North America, they're going to be associated with lower mean sea level pressure, a stronger 250 hectopascal jet, and positive IVT anomalies that are more associated with the low-level wind rather than anomalous moisture. And just briefly before I wrap up, going back to this sort of conceptual framework, you can see how the research has touched on teleconnections, on surface weather, and this work not shown on sort of the mechanisms for the formation of these regimes. And it's really about understanding as much as possible about sort of the science and what we can gain out of these regimes. Thinking forward in possible future work and expansions of this work, areas that I'd be interested in extending this is looking at the representation of these regimes in NWP models, whether that be deterministic, sort of ensemble systems, or the more nascent S2S prediction models. Inevitably, there are going to be sort of noteworthy case studies that are going to come out of this analysis. One of them is actually an early online release in MWR as sort of a subtle plug there for a paper that myself and Lance worked on. And then in addition, sort of extending this regime framework to thinking about how these patterns might change due to anthropogenic climate change and what might be occurring there. So I'll just lead these conclusions up during the questioning period. My email is at the bottom. And as a little bit of a plug, I just want to say I'm interested in postdoc opportunities. So anything that you might think is a good fit for me, I'd be happy to hear about it. And with that, I'll take any questions. Thank you.
Thank you very much, Tyler. We still have a few minutes for questions.
Thank you. Very nice presentation. So I have two questions. First one is, you have used Guan and Walliser for your ARDT. We know that we have almost a dozen ARDTs that has a global coverage right now. Mm-hmm. So have you looked into any other ARDTs? So that's the first question. And the second question is, you used the ERA interim data set for your data processing. So the ARCME project, they used MERA2, and some of the recent studies, they're using ERA 5. So have you used your methodology, like just for testing, into other data sets, and whether or not they were consistent? Thank you.
Yeah, those are good questions. So generally speaking, I've not looked at other ARDTs for this analysis. Again, given that I want sort of one of the more permissible thresholds that is out there, and not being too concerned about potentially low IVT ARs that might be more in the interior, I decided to stick with this threshold. And yeah, I've not sort of looked at some of the comparisons with MERA2 or ERA 5 and how that would influence it. Given I'm using CFSR for a lot of the other data analysis as well, anything from 1979 forward is really going to do a good enough job. But yeah, I'd be interested to see if any sort of those subtleties change the results here. Thank you.
Other questions? So how are these results going to impact predictability on a 1 to 2 week period?
That's a really good question, Morris. I like to think a lot of this is about improving situational awareness. So a lot with these, what you can sort of see with the MJO type analysis is, you have similar frequencies of the MJO where you might say, oh, we're in a phase 6 MJO. It's likely we're going to get this type of response afterwards. But I think these results sort of show that there's a broad spectrum of what can happen. And a lot of that has to do with the antecedent mid-latitude occurrence. I didn't show it here, but there's also some subtle differences in the convective signature of the MJO itself. So there's a lot of sort of subtleties that can happen here. And I think, broadly speaking, I'm interested in kind of informing people that, these have to be considered, and it's not so much MJO in this phase, you're going to get this exact response, a week, 2 weeks later.
Other questions? We have more opportunity to talk with Tyler and Alex afterwards. There are still cookies and drink and whatever. And let's thank Tyler again.